Hello. This video will concentrate upon the relationship between cell potential, electrical work, and free energy. Remember we said that with electrochemistry, we are looking at getting electrical work out of a chemical reaction or using electrical work to get a non-spontaneous reaction to become spontaneous. So now we'll really start to see how we can actually get that to happen. Remember, we talked about what actually cell potential is. The work that can be done by the chemical reaction is determined by the cell potential, by the push for electrons, or the push of electrons, and that is actually the thermodynamic force behind the cell working. So in other words, the driving force, the potential difference, or in other words, the steepness of the hill that the electrons will flow down, is the EMF value. That is the potential difference between 2 points in our circuit. A reminder that a volt is defined as a joule per coulomb. Well, a joule is a unit for energy or work. A coulomb is a unit of charge. So we can actually create another modification of this relationship. Volts represents EMF for your potential difference, and joule can represent energy, it can represent work, and charge. Now, this Q is often utilized as the variable to represent heat, as in the case of MC delta T. This is also represented as a Q. Charge is represented as a Q, but I like to show it as a Q with a straight tail just to designate the difference between Q utilized to represent heat. Zumdahl also provides this sentence, which I think is really timely, and just another way to help us understand this relationship. 1 joule of work is done when 1 coulomb of charge is transferred between 2 points in the circuit by a potential of 1 volt. So that would be the steepness of our hill. That 1 volt will accomplish 1 joule of work when 1 coulomb of charge is moved throughout the circuit, or flowing down the hill, if you will. We want to be in perspective of the system. Now remember, the EMF of our cell needs to be positive to be spontaneous, to work for us. But to get this to be positive, if we're from the perspective of the system, work is going to be negative because the system is losing work. So we have to make this equation negative, because this per our, of course, system, when we place it in there, it's going to make the EMF negative. So we need to make this equation negative. So EMF equals negative work divided by charge. But usually we are citing this to solve for work, which will then be move the negative sign over the E of our cell times Q. And usually we're looking at standard state conditions. Now this would solve for the practical real life work. Sometimes you're asked for the maximum work that's involved. Well, then we would cite the EMF of our cell that would give the maximum voltage times Q. So this is the general form that we see this equation. Okay, so let's look at an example utilizing this. A certain galvanic cell has a maximum potential of 2.50 volts. In a particular experiment, 1.33 moles of electrons were passed through the cell at an average actual potential of 2.10 volts. All right, so the max potential is 2.50 volts, but the actual is 2.10 volts. And usually, practically, you get out less than is promised to you. We have 1.33 moles of electrons. That's how we're going to get our charge. So calculate the actual and the maximum possible work done. Why don't we do maximum first? So our max work will be negative the max potential Q. Now we're not referencing or told that this is standard state, and so I don't want to go ahead and place those knots there, just in case. All right, so here would be negative 2.50 volts. But there again, how do we get Q? Well, that is where we need to learn about the Faraday. Michael Faraday did a lot of work with electricity, and he was a physicist that really founded so much toward physics, but really is respected for his work with electricity. A Faraday, to respect him, is represented by a capital F, and that represents the amount of coulombs that are in 1 mole of electrons. So, if we want the entire charge, we need to take the mole of electron times a Faraday. And here, the maximum amount of work is negative 320,000 joules, or negative 320 kilojoules. The actual will be the EQ, negative, and it's 2.10 volts, times the 1.33 mole electrons, times 96,485 coulombs per mole electron, and we would get negative 269,000 joules, or negative 269 kilojoules. Usually we get out less than we're promised. So I'd like to show you another modified way, knowing what a Faraday is, of this equation. We can also say that work equals negative E naught NF, which N represents moles, of course, and F is a Faraday. So we need to be familiar with both forms and how to interchange between them. All right. Yay! I know that Devin, you're especially excited, Devin Berry, for free energy. So, the relationship of potential to free energy. Okay, now, remember we said, what is free about free energy? And we said that it is the energy available to do useful work. The energy available to do useful work. Okay, so, if the amount of energy available is Gibbs free energy, well then, if we know that max work is negative E max Q, well then that equals delta G. Remember again that Q is NF, so the way that this equation is usually represented is that delta G is negative E NF. Now, remember something else about Gibbs free energy. When Gibbs free energy is negative, the process is spontaneous. When it is positive, the process is non-spontaneous in the direction written, or the way we have our anode and our cathode identified. So, we want the E of our cell to be positive. Of course, these guys are going to give us positives. And so, as long as this is positive, it's going to deliver a negative delta G, which will make our process spontaneous. Okay, so let us see where this equation will be used. Look at this problem. Using standard reduction potentials, calculate delta G naught for the following reaction. Is this reaction spontaneous? All right, so what we need to do is calculate this and then determine, based upon the sign, comment if it's spontaneous or not. So, we have copper plus 2 going to neutral copper. This is being reduced. We have our iron going to iron plus 2. So if we want to complete 1 copper plus 2, so we have 2 electrons. 1 iron, fantastic, but we need 2 electrons here, and great The number of electrons in the reduction equals the number in the oxidation. Now, what we need to do to get the E of our cell, which we need, of course, to calculate delta G, we need to cite the table of reduction potentials. And when you look at this reaction, copper plus 2 electrons yielding neutral copper, you'll find that the E of that reduction is 0.34 volts. But then, of course, this is the oxidation. So we define the reduction of iron plus 2 electrons yields iron neutral. Flip the sign because it's representing our oxidation, and that becomes positive 0.44 volts. So good, so good. Looks good so far because we have a positive 0.78 volts. We really don't need the balanced reaction as long as we're good there. This is what we need. So, now something that we need to make note of is that the total number of electrons is balanced. And we'll need that in just a moment because we need that for N. So we found the E of our cell, 0.78 volts. We are involving 2 moles of electrons unless otherwise told about concentration. And per the Faraday, it's 96,485 coulomb per mole of electron. This gives us negative per sig fig 1.5 times 10 to the 5th joule. It doesn't say anything about can you leave it in joule or not, but we know that Gibbs is usually in kilojoules. So negative 1.5 times 10 to the 2nd kilojoules. The negative means that it is spontaneous, which is confirming the relationship with a positive E of our cell. So we've answered the question. So it is spontaneous. Oh, that was a little bit crazy. So the cell is spontaneous due to negative delta G and positive E of our cell. These are standards, so we would say standard, 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 standard. Okay, let's look at another neat example. I remember when my husband got me my engagement ring, the jeweler had asked me what I did for a living when we went to get it sized, and I said I was a chemist, and he said, "Oh, make sure that you stay away from acids." So let's see. Using standard reduction potentials, predict whether a 1 molar nitric acid solution will dissolve gold metal to form a 1 molar gold plus 3 solution. So, is it the gold that we were worried about or the diamond? Okay, so to attack this problem, we are worried about gold forming gold plus 3. All right, when we look at this reaction, standard state for this oxidation is negative 1.50 volts. So we know not too favored to happen. Well, we would need our nitric acid, which we know, being a strong acid, exists all as hydrogen ion and all as nitrate ion. So we have to look at our different reduction reactions and see, is there one that involves nitrate and the hydrogen ion? And there is. Nitrate will take on 3 electrons to form nitrogen monoxide and water. And that is 0.96 volts. So, how perfectly balanced we are with 3 and 3. When we add up our E of our cell, it is negative 0.54 volts. Already showing us not spontaneous. So just to confirm, and we really can only truly address that by calculating delta G, and because these are standard state, I would do delta G naught is negative NF, and this is, of course, E of the cell. Okay, we have 3 moles of electrons times the Faraday times the negative 0.54 volt, which is a joule per coulomb. Coulombs cancel, moles cancel, we're left with joule, and this gives us a positive 160,000 joules, or a positive 160 kilojoules per mole, non-spontaneous. And so this reaction would not happen. And so if the gold was dropped into nitric acid, a reaction would not occur. A reaction would not occur.